Are you guys talking about me or Professor Tabor? Okay, so Professor Tabor, but strangely, I can hear him pretty well.
I can hear you.
They said it's pretty low. Um, maybe you can turn up the volume a little bit more, or
I'm
move
not
closer
quite
to your
sure how
speaker, to your phone.
I'm not quite sure how to do that, and I don't want to find that I've totally lost things.
Maybe moving closer to the microphone.
Well, I've got the microphone on the headset here. Is that
Okay.
is that any good? How does that sound?
A little better.
Right. I mean, the only thing I could try.
Is this better?
Oh, this is better.
Ah, good. I wonder if it was picking up the microphone on my laptop rather than on my headset.
Yeah, so that might be the problem.
Yes.
Anyway, for the interest of time, let's get started. I look forward to your training section. So Professor Tabor, please take it away.
Thank you very much. The next question, of course, is can I work out how to share my screen?
I think you can because
there we go. Yep, hopefully. I hope you can now see I have some slides and I will put them on like that. I hope everybody can see that. I'll put that over there. Right, okay, yes, thank you very much for attending my training session. I had enormous fun putting this together, and I hope you have as much fun making use of it as I have putting it together. What are the aims of this session? Well, I described this as an intermediate level session, so I'm going to assume you have some knowledge both of computational fluid dynamics and of OpenFOAM. I'm going to start fairly basic level, but also go to some fairly challenging and high-level stuff during this presentation. Obviously, I want to describe as far as possible the range of turbulence models available, and OpenFOAM has implemented quite a range of RANS, LES, and DES models by now. I'm obviously not going to have time to talk about them in any great detail, but I'd like to mention at least all of them. And there are some which I'm going to go into in rather more detail because I think they're not so well known, but are quite interesting. I'm hoping to demonstrate their use. I've put together a tutorial example on the backward-facing step. I know that backward-facing step tutorial examples are all over the place, including several in the main tutorial section of OpenFOAM, but this I have deliberately based on some experimental and numerical data very recently published, and I hope to be able to go into it in quite a lot of detail to show you how it's put together. If we've got time, I've also got an example for a large eddy simulation of how to simulate a Taylor-Green vortex, which might be of interest. I'm also hoping to show you some useful OpenFOAM commands, things like foam info and some features of the command line system for post-processing, in fact post-processing in general, to show you some of the things which might be useful if you're trying to run turbulence simulations. And I'm also going to show you some function objects, once again, which might be useful if you're trying to set up a turbulence calculation. And some of that will involve programming and some fairly detailed investigation of OpenFOAM in that area. So I'm hoping that whatever level you're at, you'll get something out of this session. I will try and remember to keep an eye on questions and give you a chance to ask questions as we go along. If I'm going too fast or I start pointing at things on my screen or anything like that, then please somebody shout at me and I'll try and remember that I'm online and not in a lecture theatre. Okay, I mentioned this backward-facing step case. It's based on a particular research paper published last year in Water Science and Engineering, and I've got a copy of it here. It's a fairly standard case. They're largely focusing on large eddy simulation, but they're comparing against experimental data which they provide, and also it provides a very nice geometry to use for this. I'm keen to provide the case files once I've worked out the best way of doing that. If nothing else, I can put them on Dropbox, and if you send me your contact email address, I'll share the link with you that way. I've produced some case files for the RANS case in 2 dimensions, so we can look at how to set up a RANS simulation for that. And I've also extended it to do a full 3D large eddy simulation case. I'm assuming that if I'm using OpenFOAM version 7 on this, that's what I've tested it on. I hesitate to say works on OpenFOAM 7, but I haven't found major bugs so far. It may work on the most up-to-date versions of the other forks of the code, but I can't guarantee that. And if you've investigated and find there are issues, then do let me know. I'll see what I can do to help you resolve them. And as I say, here's the geometry. It's a very standard backwards facing step height of 5 centimeters, which is half the total channel width. The entire length of the domain is 2 meters, and I based my mesh on the mesh resolution used in the paper. So downstream of the step, you've got 210 cells in the X direction and 40 cells in the Y direction. And for the LES cases in 3 dimensions, I've extruded the mesh out to 32 cells in the Z direction there. Okay, I hope that's given you an orientation of what we're doing here. So I wanted to, as you can see across the top here, my slides are divided into 3 sections: a short overview of turbulence modeling, followed by a much longer or a much larger number of slides on RANS models, and then slightly fewer on large eddy simulation. And I'll intersperse this with trying to run some of these calculations and show you how the commands actually work in practice. So I spent a certain amount of the last few days trying to sort out, in my own mind at least, how turbulence models fit together. And I hope you've all got some knowledge of this. I eventually decided a mind map would be a sensible way of doing things, so I'm not completely convinced I've got it right yet. I'd like to improve this, but this is the current state of my mind map. I think the various captions need to be a bit larger here, but you can see we've got turbulence, which is what we're trying to simulate here. And then various things in yellow represent the main approaches to turbulence modeling. So direct numerical simulation, full simulation, which is not typically very useful in engineering. And then you've got ensemble or Reynolds averaging, which gives us our RANS equations, or alternatively volume averaging for filtering, which gives us our large eddy simulation. Those two can combine to give detached eddy simulation, whilst RANS itself breaks down into eddy viscosity models, and these are things like the well-known K-epsilon model, and Reynolds stress models, which are somewhat more sophisticated, potentially more accurate in complex cases, but also correspondingly more challenging to actually run. And the boxes around the outside in a sort of turquoise blue color there represent the end product, what you actually interact with, the different turbulence models which we're activating and using. I've tried to indicate how those fit together in terms of different classes. And I'll talk a little bit about these different ones in the next few slides and throughout this training session. I'm going to mention something which will probably come out a lot more on Friday, because I know Fred Mendonça is going to talk about this and there's a community session. But OpenCFD has recently established this OpenFOAM governance system, which is intended to enable the community to contribute to the development of OpenFOAM. And in particular, there are a number of technical committees, one of the most active of which is the Turbulence Technical Committee, which is being headed by Charlie. And Charlie has set up this this online questionnaire. I can click on there and it takes me to an OpenFOAM turbulence modeling survey. And I would encourage you after the session to follow that and to identify for our benefit what turbulence models you're using. But about a week or so ago, he gave me some results from about 221 responses, and this shows you what they are. Basically divided into RANS models versus LES and DES models. Interestingly enough, the most popular RANS model seems to be the K omega SST model. That slightly surprised me. It's a great model, but I guess I hadn't realized it had taken over from K epsilon as the most popular one. Standard K epsilon seems to come in second, and then you can see some of the other ones there: K omega, realizable K epsilon, Spalatel Maras, and so forth. I think the LES models, interestingly enough, the majority of people don't use LES. That's fine, no problem there. To my surprise, Smagorinsky came out as the most popular choice, despite its reasonably well-known flaws there. Whale is another model which is fairly recent, and I'm hoping to give you something of a quick tour as to what Whale stands for and what it, how it operates. Dynamic K equation, various K equation simulated model there, and various DES models as well. Okay, so some comments here about how we implement turbulence models here. And if you've done any programming or have been to any of the programming sessions in this workshop or in previous sections, workshops, you hopefully have some idea as to what's going on here. You know that OpenFOAM is a code written, or rather it's a code library, and it makes use or extensive use of the features of the C++ language, the object-oriented features of C++. And in particular, a lot of things that we use in OpenFOAM are classes, things like the mesh, vector fields, vol vector fields, and so forth. These are all classes which have been developed by the authors to write the CFD codes. Now, you can see how things like a vector field would be an obvious class, but the process of using object orientation continues higher up. And in fact, all of our turbulence models are themselves classes. And there are reasons for doing this. Now, as I'm sure you're aware, when you learn about turbulence modeling in CFD, you learn about doing an averaging operation to reduce the complexity of the problem. And if you apply that averaging process to Navier-Stokes equations, you end up with a very similar set of equations with a term divergence of R, which we don't know. This is the closure problem, and this is the term we're trying to model. So we conclude from this that all of our turbulence models have to give us a div R term in some form. The reason why we have the individual turbulence models as classes, they can derive from a virtual base class, which makes it important, which makes sure that anybody writing a new turbulence model class has to do it properly. They have to provide this additional term. More specifically, it returns a particular type of matrix object, which can go into the general matrix object you're trying to assemble here. So in OpenFOAM, all our RANS turbulence models, and in fact all of our turbulence models in general, are descended from the same base class, same virtual base class, which gives them the same class interface and means that if you write a new one, you can easily plug it into the same system. Also means that we've gone runtime selection. The base class itself is referred to by a pointer, and then at runtime you can choose which model it points to. So if you open something like in this case PiezoFoam here, you can see in the one of the header files the creation of the pointer to a turbulence object, and then when you look at the momentum equation, you'll see this additional line here, turbulence points to div dev ref u, and that's where the turbulence model enters into the average momentum equation. I'm not going to go any further about programming at this stage. I hope that was an interesting diversion for those of you who have tried programming in OpenFOAM, but it may not have meant much if you haven't tried that yet. There will be further programming later on in this session. Anyway, the main turbulence solvers here are, well, in the incompressible case, you've got simple foam, obviously, standard simple based non-transient, so steady state code there, and you've got two codes which are transient. So you've got PiezoFoam, which is a standard piezo algorithm, and then pimple foam, which of course is this blended algorithm. Of course, so OpenFOAM does also have a facility to run compressible calculations, and you can recognize the codes because they start with rho typically, and there are the equivalent there, so rho simple foam, rho pimple foam, rho PiezoFoam, and a slightly different algorithm, rho central foam. And our turbulence models can be either incompressible or compressible according to which solver you're using. Most of the turbulence models are the same in both categories, and I kind of understand there are moves towards homogenizing the whole lot together. To be honest, for today's session, I'm planning on just sticking to incompressible flow. We've got enough problems running turbulence without adding compressibility to the mixture there. You're probably aware, if you look at other codes in the library, particularly in things like multi-phase flow, they often have hard-coded turbulence models which are not part of this structure. So I'm also going to ignore those as well. Again, I think there are moves afoot to homogenize things as appropriate. Okay, so do you really need me to do this? Well, you can actually find out a lot yourself, and there are various commands in OpenFOAM. In particular, you can find out what turbulence models are available for any particular code by typing the code name followed by this flag list turbulence models. Actually, you can do this for a number of different aspects of the code. If you want to find out boundary conditions, you can list scalar BCs, for example, or list vector BCs. But at the moment we're looking at simple foam, let's say list turbulence models. Why don't we do that? I'll just transfer over here. I will, sorry, I was just doing something there. Don't really need to be here. Open. F7, I always forget to do that and then wonder what's going on. So simple foam list turbulence models. There we go. This is where you find I can't type. There we go, and it's printed out a long list of the turbulence models. You used to be able to do this by what one of my PhD students refers to as the banana test. So put banana into one of the dictionaries and see what error message you get. But now you don't have to do it that way. You have this feature list turbulence models, and you can see it divides them up into Reynolds averaged versus LES models. What else have we got here? Well, FOAM info is another useful command, and once again, it's generally useful. It interrogates the header files for OpenFOAM and gives you the information provided there about whatever it is you're trying to find out about. So in this case, we can use it to find out about particular models. So for example, let's assume you're interested in the QZeta model, not a very well-known model, I think, or less well-known than K-epsilon. So FOAM info, oops, sorry, QZeta, like that. And it's printed out what is actually in the header file for the QZeta.h, a header file there if you go look for it, but it's a more convenient way of finding it. So you find that QZeta was produced by Gibson and Dafa'ala, gives you a couple of references to the papers it's based on, and very often gives some information about the model itself. So info, okay, try another one, K-epsilon, there you go. You can see here, trying at K-epsilon, there are several different entries here, so you can choose which one you think is most appropriate, and it will give you the information there, including a list of tutorials which use that particular model, which is really quite useful. You can see here there's more information about the K-epsilon turbulence model, including rapid distortion theory terms and so forth. So that's really quite useful. As I say, it includes reference papers for the implementation. And one paper which comes up very frequently, so I thought I'd mention it, is not actually a research paper. It's somebody's, it was David Apsley's personal homepages at Manchester University. I put the link in there, and my impression is that somebody, probably Henry Weller, was using this last time they updated the turbulence models in OpenFOAM, because it's a pretty good summary of most, if not all, of the turbulence models in OpenFOAM at the moment. So you might want to have a look at that just generally. You've got the coefficients, you've got viscous terms, notes on them, and so forth. It's quite a useful source of information. Okay, let's go back to the presentation. I did mention also here there is this command FOAM search, which you can use to list models used in particular tutorials, so you might want to have a go with that at some point. So I spent a happy evening playing around with FOAM info and extracted the information. I was about to say, so you don't have to. I hope you do at some point, because I haven't pulled down all the papers and so forth. But just to give you a quick whistle-stop tour of what we've got, I've tried to list everything and to group them into different categories. Now, fairly obviously, K-epsilon, big area of modeling here. Got standard K-epsilon model. It dates back to the mid-70s. I put the dates in here to give some feeling as to the age of the different models here. So standard K-epsilon model, high Reynolds number with root functions. RNG K-epsilon model is a bit more recent, 1992, and of course the point about RNG was it was a way of evaluating the coefficients. So the coefficients are different, and there's at least one extra term in the model, and this tends to make it more responsive to instabilities in the flow, which means that it's probably a good choice if you're doing something where you've got vortex shedding occurring. Then you've got the realizable K-epsilon model. I don't know how much you know about the theory of turbulence modeling, but the K-epsilon model equations are not physically accurate. They change incorrectly as you go from one frame to another. Realizability means you formulate those equations in a way which is physically accurate in all frames of reference, including rotating ones. So the realizable K-epsilon model, again, well-known model in the literature, 1995. And if you've got a rotating system, so an impeller or a turbine or something like that, that's probably a good model to use. Then you've got the problem of low Reynolds number flows. I'll talk a bit more about near wall modeling in a minute, but a lot of the distinction here is between a standard high turbulence boundary layer and a less turbulent boundary layer. And there are various models in the library which have been developed specifically for doing low Reynolds number flows with wall resolved modeling in some form. So you've got 3 versions of the standard Kapsilon model, developed by Lamb and Bremhorst, by Launder and Sharma, and Leon Leschinger, Mike Leschinger there. And they have different approaches, all roughly the same. So high resolution near to the walls. The Launder-Sharma model was developed for internal combustion engines and includes these rapid distortion theory terms to take into account the compression effects there. Whilst Leon Leschinger's model has near wall damping and will run for both low and high Reynolds numbers. Also there, which we just had a look at, the Q-zeta model, another 2-equation low Reynolds number model. I think, again, it will do low and standard Reynolds number flows. I've titled this slide Other Models. I couldn't work out what coupled these all together, except I couldn't find them anywhere else, or put them anywhere else, obviously. K omega and the development of that, the K omega SST model. K omega is the standard one from Wilcox, using omega rather than epsilon as a second variable, whilst the SST variant blends that with the standard Kapsilon model in order to get something which works for exterior aerodynamics. So K omega you can use on an interior, a duct type flow, but the model has problems with far field if you've got an exterior aerodynamics problem. The K omega SST model solves that problem by this blending process. If you're doing exterior aerodynamics, and particularly if you're going to do airflow over a wing, for example, you're probably going to use the Spalart-Almaras model. It's a 1-equation mixing length model, basically solves directly for the turbulent viscosity as a single transport equation, highly respected for lift and drag calculations. And then I'm going to talk a bit more about this in a minute, but a new, relatively new model, V2F, and this is a modification of a basic eddy viscosity model, a basic K-epsilon model, in order to try and account for anisotropy. Anisotropy in turbulence, of course, is a big issue, and we want to find some way of dealing with it, and that tends to involve Reynolds stress modeling, and so that takes me on to Reynolds stress models in OpenFOAM, and there's an algebraic Reynolds stress model developed by Xi and 1 or 2 collaborators there in 1983, and a couple of differential or transport Reynolds stress models where you're solving a transport equation for the full, I was about to say 9-component, actually it's a 6-component second rank tensor. Now obviously this is somewhere where OpenFOAM really scores. Other codes you have to implement each component separately. In OpenFOAM we can write down one transport equation for the whole tensor, which is absolutely delightful. So you've got one from Launder, Rees and Rode in 1975, transport equation for this Reynolds stress term, and then one which is claimed to be an improvement, slightly different modelling here from Speziale, Sarka and Gatsky. So that's, I will just see, I'm not 100% certain how to check whether or not there are any questions at this stage. I'm still trying to...
Professor Tabor.
Yes?
I don't think there's any like a technical question at this point.
Yep.
But I do ask anybody have a question, please type in the chat box, and then we can end those at the end of the presentation. So,
right.
Yeah.
I may have to rely on you to tell me if there are any questions in the chat. Ah, there we go. Okay, it sounds like beyond the problems with Yes, yeah, I will certainly share the presentation. I will put together a zip file of the case files and this presentation because it explains everything. And I'll even throw in the Wang et al. Paper so you can see what we're working from here. So hopefully that's useful to everybody. Okay, so how do we actually implement this? Actually, how do we actually use this? Well, I'm sure you're probably fairly well aware of this, but just to make sure everybody knows what they're talking about here, we use dictionaries, obviously. So in constant, everything which is physical modeling goes in constant, as against things which are numerics based, which are in system directory. So in constant, there is a dictionary called Turbulence Properties, which, as you might expect, tells you how to, or describes what turbulence model you want to use here. I did a quick screen capture here to show you a typical one here. So there's a keyword simulation type, and that can be RAS for RANS or LES for large eddy simulation. Based on that, you expect to find or provide a subdictionary, either called RAS if you're running RANs, or LES if you're going to do LES, obviously. And this has switches to select the model. So RAS model, you specify which turbulence model you're after. Turbulence switches the turbulence simulation on or off. I'm slightly uncertain why we need that and laminar as a model, but never mind. And finally, print curves. Obviously, coming back to the programming, we have this policy, or C++ has this policy, that we want to declare variables or class instances. We want to initialize them before we use them. So all of these models have in their implementation the standard value of the various coefficients. If you put print coefs on, the first thing the turbulence model will do when you try to run it will be to print out those coefficients. You can also optionally override those coefficients by providing a model name coefs subdictionary. So in this case, this is running k epsilon, so I've got a k epsilon coefs subdictionary, and I can use that to override the coefficient variables. But that's higher level stuff if you need to. If you're just starting with turbulence modeling, you're probably not going to make use of that. Okay, so a little bit about wall modeling. We implement the standard high Reynolds number formulae, so based on the logarithmic formula for the near wall flow behavior. And from that, you can formulate the wall shear stress, or wall shear velocity rather, and values for K and epsilon, and in fact omega, which can be used in the appropriate fields for the appropriate boundary conditions there. And this avoids us having to refine the mesh that much in that region. More recently, in my terms that is, of course, people have extended this. You don't have to restrict yourself to a logarithmic law here. You can go into the laminar region where the velocity is linear and the k value is quadratic with distance from the wall, like that. And you can formulate wall functions which use these formulae or switch back to standard wall functions locally based on the local cell y plus value. So we want to implement these onto our specific quantities which we're solving for, so we need boundary conditions for the different turbulence fields. When you're running a turbulence calculation, you're going to set up a new T file. So new T is the turbulent viscosity field here. So you need wall functions to deal with this, of which I think U Spalding wall function is the standard high Reynolds number version, and I suspect T wall function switches here. If you want to check this, go and use OpenFOAM info. I should have planned that, but you can go and do that. For epsilon, for omega, and for K, Q, and R, there are similar wall functions which implement the high Reynolds number logarithmic law of the wall type of thing, and there are the low Reynolds number versions which implement this switchable thing in terms of the switching between the laminar and the turbulent wall function there. I can see a number of queries about this. I will come back and try and answer them in a minute. Don't go away, so to speak. Of course, the alternative to high Reynolds number, to wall modelling rather, is simply to resolve the boundary layer and use a low Reynolds number model. We've mentioned one or two of them so far. This requires a higher mesh resolution, y plus of around 1 throughout, and alterations to the turbulence model. For example, introducing wall damping terms, a wall distance dependent function f, which damps out the turbulence close to the wall. However, generally said, there's no explicit wall modelling, and of course you are resolving the flow in the wall as a result of that. What other aspects of boundary conditions do we want? Well, obviously K, epsilon, omega, and so forth are all elliptic fields, or obey elliptic equations. So we're going to need to specify the values at the inlet. You're probably aware that we could do it just by specifying value of K at the inlet, value of epsilon at the inlet, but typically we don't know these things, so we use rules of thumb based on simple heuristic equations which people accept. So for example, you can specify a turbulent intensity I and specify the inlet turbulent kinetic energy as that fraction of the resolved kinetic energy. You can do a similar thing for the epsilon value at the inlet, and for that matter the omega value at the inlet. So we have these boundary conditions, turbulent intensity, kinetic energy inlet, and so forth, which implement these things automatically, and that can be quite useful. Now, I said I wasn't going to go into too many details of the individual models, but there were a couple where I felt they were not so well known, but potentially quite interesting. And I had the slides from my own lecturing at Exeter, so I thought I'd shove in a couple of slides on a couple of specific models. And one of them is this V2F model, which you may have come across. It's a modification of a basic eddy viscosity model, in fact the basic K epsilon equation model, but to try and account for the anisotropy in the turbulence, particularly close to walls. And does this by trying to model one of the Reynolds stress components. That's the V squared bit. It's a component of the Reynolds stress parallel to or along the streamline and therefore along the wall, and we can write down a transport equation for this. There's also a relaxation factor which is used to relax the modelling of that close to the wall. And based on this, you can write down a turbulent viscosity. Well, of course, you've now got not 2 equations, but 4 equations, because you've still got the K and the epsilon equation. So you've actually got the potential to form several different turbulent length and time scales. And so the model switches between the K epsilon length and the V squared F length, depending on which is the largest, and does something similar for the time scales, and then implements the turbulent viscosity as given there in the equation. And just for your interest, those are the transport equations of V squared and the elliptic equation for F, which are being solved alongside the standard K epsilon equation. Boundary conditions, we obviously need some additional ones, use standard ones for K and epsilon, but V squared and F need new boundary conditions which have been provided. And we also need to specify inlet values. So V squared, 2/3 of K, you can see that from the fact that it's basically a Reynolds stress, and the normal component of F is 0, so 0 gradient at the inlet there. The OpenFOAM implementation of this, by the way, is given at this reference, Davidson and his collaborators there, and it's a model which is aimed to be usable for both low and high Reynolds numbers. Okay, I will have a look at the group chat just here. Turbulence models for GPU. I don't know of anything there. It's difficult. The thing about GPUs, of course, it's a very different approach it needs a very different approach to CFD in general, because CFD, the way we do it in terms of domain decomposition, the parallelization works best on a small number of very fast processors, whereas a GPU provides a large number of very poor processors. I would imagine that you would not want to develop a turbulence model for GPU because you need to be able to run or you would not develop just a turbulence model for GPU. You'd want to run the whole code on a GPU. So I'm not aware of anything there. Can the turbulence model cause numerical oscillation in compressible flow cases? If so, how to avoid it? In one case, I had smooth velocity for K epsilon, but it was high sheared flow, and I had to use realizable K epsilon, but the solution started to show some sort of unsteadiness. Yes. In turbulence modeling and in CFD, you can have stable, fast, or accurate. Pick 2, basically, or possibly even pick 1. Yeah, there's always this trade-off between stability and accuracy in particular. If you think about it, a turbulence model basically raises the level of viscosity in the flow, in the simulation. We all know what viscosity does to a simulation. It stabilizes it. So K epsilon, basically, it's putting a lot more viscosity into the problem, so it's solving to the lower Reynolds number, where it's smoother and more stable. If you go, but that's not necessarily accurate, and K epsilon is exceptionally stable because it puts in an exceptionally large amount of turbulent viscosity. If you go to more accurate models, you're very often doing the trade-off of lower viscosities and therefore more unstable. So yes, I find it only easy to believe that if you're working on the realizable K epsilon, then you are going to experience more instabilities than the standard K epsilon. A useful tip with this, particularly for things like Reynolds stress models, is to produce a converged model using K epsilon and then switch to the more accurate model to finish it off with, because then you're not having to evolve from your initial conditions, you're evolving from a flow field which is close to what you're actually expecting. Also, you've got to think, is your solution actually unsteady? Is your case actually unsteady? I'm going to confess here, I have an exceptionally high cutoff for the, I'm going to be running my backward facing step with a very high high value for the convergence criteria, because I think because it turns out it doesn't converge on what I would regard as being a good value there, because I think the velocity field is probably unstable. It's probably a transient flow, but I'm trying to run it using simple foam. It's quite likely if you've got a rotating problem or something like that, it's unsteady. Raw modeling implemented for power law, yes, that's certainly the case, just gone through that. Turbulence models for statistically instationary transient flows of the world, blah, blah, blah. I'm guessing here you want LES. I'll come to that. Maybe we could talk later. Reynolds number cutoff to determine if I should use a low Reynolds number or a high Reynolds number case. Well, It's more question. Well, that's a good question because I'm going to be going on to that in a minute here. Sorry, on to that in a minute. This slide is a good one for this. Basically, you want to look at the Y+ values. Now, we're familiar with how the structure of the boundary layer looks. You've got a laminar sublayer, transitional region, and then log law region. And the log law region is sort of from Y+ is about 30 upwards. So from 5. The logarithmic law bit is a particular Y+ value onwards, and we need to check that our cells are sufficiently large that they contain a significant amount of that log law section. And we tend to suggest this in terms of no Y+ value should be less than 11.6. That's the criteria. But actually, it's easier to do it in terms of averaging. So you look at the average Y+ value, and maybe 30 to 50 is a good value there. And if you can't get that, then you probably have to consider a low Reynolds number model. So how do you actually evaluate this? Well, it's the sort of thing where you have to be a bit cyclic here. You can't work out how fine the mesh needs to be in the abstract before running the calculation. So you have to set up a mesh, run the calculation, and look at the Y+ values. And there's a tool to do this. It's part of the command line post-processing interface, but it needs to extract information about the turbulence model. So you need to run it using SimpleFOAM. So you've got this command SimpleFOAM, post-process, and then various functions. You've got the function, the turbulence intensity, so it will calculate your value of I throughout the flow field. You can also calculate the wall shear stresses, which might be useful for your physiological airways there. So you can do that using a function called wall shear stress, but you can also calculate the Y+ values. These will be on the boundary patches, and you can average them afterwards and have a look at them. So I think this is a good point to switch over and actually run some of this. So let's have a look. I've got a directory here with my backward-facing step case here, 0 times step directory, constant and system. Let's have a look at some of the values we've got here. Where should we start? Well, let's start off with what turbulence model are we running here. You can see here, Reynolds average, Navier-Stokes, kept epsilon. I'm expecting it to print out the coefficients, which is absolutely fine. I've set up the viscosity correctly for that. I've set up in the 0 times step directory here. Obviously, I've got all of my usual files for my different variables here. Ut, open, there we go. And you can see I'm using standard new TK wall function here, and I've specified 0 in internal field and so forth. What else have we got? Epsilon K, let's have a look at the K field here. And once again, using the standard wall functions here. Possibly now I'm looking at this, I'm thinking possibly I should be using the switchable wall functions. I'll have a go at that afterwards. But I've also implemented the inlet. You can see originally I just gave a fixed value, which was wrong, unfortunately. But I've put in using turbulent intensity kinetic energy inlet value here, and quite a high value for the intensity here to do it more accurately. And then epsilon, same sort of thing. You can see here, what have I got? Once again, I've got my wall functions set up, and I'm using the turbulent mixing length dissipation rate inlet setting there. I've set it up with a standard block mesh, so I can block mesh this. Where am I? Yeah, so I run block mesh and it creates my mesh for me, and I've set up a control dict to run for 1,000 time steps. sorry, 2000 time steps actually. And I've done what I usually do. I'm going to run simple foam, so I set delta t to 1. So instead of having time step directories, I've got iteration directories basically. I like to do that. It kind of keeps things nice and simple and neat. So simple foam, run it like that and sit back. It's actually running quite fast. I updated my laptop at the beginning of the year, which was good timing as far as I was concerned. Anyway, you can see if I'm running geometric algebraic multigrid here. It's running pretty fast. It's a few thousand cells in the mesh, which is perfectly okay. And it actually converges, but to a very coarse tolerance in about 900 iterations like this. Or as it did earlier on. There we go. So let's have a look at the results here. So open up Parafoam in the usual way. Close that. Let's see. 192. Pull in mesh there, volume fields. And you can see here that my mesh is basically two-dimensional. If I do surface with edges, you'll see that's one layer of cell thick, which I can get away with for RANS models. And if I plot the velocities there, you can, I'll get rid of the surface, the edges there. You can see a very nice example of a backward-facing step. Back like that. You can kind of see here, you've got the inlet flow going in this direction and some kind of region back here. Now, we're probably aware that's a recirculation, but let's show it a bit more accurately or a little bit more nicely. So filters, what have we got? Stream tracer, that would be a good one to use. I'll point it in along the y-axis. There we go, and start from 0.2. I have obviously been checking these settings, which is why I'm able to find them so quickly. So I do 50 resolution there. And you can see that given quite, in fact, I'll change that slightly further, put them there, why not? There we go. And that's given me a rather nice recirculation zone here. I'm going to let's have that as the feature edges to give the edges like that and zoom in a bit. You can see that's very nicely produced my recirculation region. Of course, if you're interested in the recirculation length, which is somewhere around here, you might want to plot things along this boundary here. What are we going to have a look at? Well, obviously we can run some of these post-processing things afterwards. So let's try, just to demonstrate I'm actually doing this. If we look in, oh, that's 992, for example, you can see those are the files I've got here. So simple foam, post-process. What should we do? Y plus, why not? Oops. You see it's read in and written out Y plus values. There we go, there's my Y plus values. I could plot those in ParaView, obviously, but it's also printed out the average values here. And you can see it's probably a little bit low, which is possibly why I'm having difficulty converging this particular problem. I think before I distribute this case, I'll go back and have a look at my boundary conditions on that. Obviously, I can do these other things. I can post-process and produce turbulent intensity and wall shear stress from that. Now, I thought I would challenge myself and do something a little bit brave here. This is the K epsilon version. How about K omega? Let's switch turbulence models. So I do this to my students, so I thought I'd have a go with it myself here. I'll get rid of that actually because I want to do it from scratch. Let's copy this and produce a new version. Paste, there we go, it's a copy, rename as There we go, omega. Open this. Oops. Now, omega obviously has different dimensions. So it's a frequency, so it's 10 to the -1 there. And I'm going to convert these to function, which has a slightly different thing there. So I could probably do this in a slightly better way by using various of the pre-processing directives, but I didn't set it up that way. Again, maybe I will do that before distributing it. There we go. And turbulent mixing length. Frequency inlet, of course. There we go. Running simple foam. Oh, worked. I would normally have to, obviously I also need to change various of the other settings here. In particular, in FV schemes, you might find that you don't have the correct schemes for solving the omega equation, so you may need to swap those over. I'll tell you why that's running. I haven't switched the turbulence model. My apologies. This is why I don't like doing these things with people breathing down my neck. Sorry. Okay, let's do this again. My apologies there. Okay, I'm going to switch this to the K omega model. There we go. So run simple foam, and it's told me that I haven't specified the correct numerical settings for the differencing schemes, which I haven't. I was aware of that, so I need to go to FE schemes. And what I'm going to do is where I've got epsilons, I'm going to convert them to omegas. The epsilon F becomes the omega F. It's basically the same numerical equation I'm solving, so I'm keeping the same numerical scheme. And I would probably also have to do the same thing to the numerical things here. So epsilon, I want to solve an omega equation, like that. And then lower down, we're running simple, so I need to have appropriate relaxation factors. And I had a heart attack this morning when I forgot to add a relaxation factor for omega. I couldn't get the thing to converge at all, as I might have expected. Well, it took me half an hour to spot that I'd made a mistake there. Okay, so now it should work. So hopefully, yeah, there we go. Now we are solving the same problem, but with the omega, K omega equation rather than the K epsilon equation, which is excellent. Anyway, I want to carry on here because, so any other messages here? Y plus, of course, would be calculated with the local velocity, not the mean velocity. I mean, it's a local property. And genuinely don't know. There used to be a Y plus LES code to do this. I think now, if you're, because of course you would run post-process func Y plus with the code you're running it with, that probably takes account of that. The Kunden, I think I might come back, please contact me about the Reynolds stress and OpenFOAM. Yes, that would be very interesting. I've done quite a lot on high swirl flows for cyclone separators. Please do get in touch with me. I'd be interested to talk to you about that. Okay. Well, just to mention here, I've mentioned that it's often a good idea to restart from the existing field, and I was able to construct an omega field by hand, but obviously Reynolds stress would be a lot more complicated, but there's another post-processing function to do that. If you use func_r like this, it will write out Reynolds stress fields based on K and epsilon inputs, and you can use this to generate an appropriate R-vol tensor field for a restart with the Reynolds stress. I'm not going to demonstrate that, but you can use it like that. What's one thing I was going to mention? This comes into the category of really advanced stuff. If you read Wang's paper, you realise that the inlet is not uniform. At the moment, I'm just specifying a uniform inlet velocity, but actually the flow is coming from a duct upstream and has had time to develop some kind of a boundary layer, which he's measured. So we really ought to be taking this into account. And in fact, in his paper, in their paper rather, he and his collaborators fit the experimental data to this solid line, which is given by this slightly complicated exponent function. And yesterday I was thinking about this and I thought, yeah, it'd be quite fun to actually do this properly. So how can we do it? Well, as with it was the case with OpenFOAM, there are often lots of different ways of doing the same thing. You could do it by writing your own boundary condition, but that would be quite a lot of work, not too difficult. You could do it by specifying measured data. There's a boundary condition for specifying a lookup table, I believe. But also there's another one which enables you to do some coding at runtime. And it's called coded fixed value. I thought it might be quite nice to show you it in an operation. So it's basically a new boundary condition. So you've got your usual thing, you give it a name, the inlet condition we're trying to do here, type coded fixed value, a value which is a dummy in this case, although I left a slightly odd value for the inlet there. And give it a name, redirect type, names it inlet profile, and then if you look at the code, you will see that between there are two hash marks here, and there's a block of C++ code between them, which is going to be compiled and run. And in fact, I have created a separate case here. So BF step coded fixed value implements this on the velocity. So let's open the U file here. So here's my inlet boundary condition, coded fixed value, and here's my code. Now, in order to get this to work, I obviously need to go through my inlet patch, find the value of y, and evaluate one of these two expressions based on what we've got here. And that's exactly what's going on here. So we are doing this for a vol vector field, so it will have a reference to the underlying mesh structure of the patch it's attached to, and from that you can get CF, which is the normal vector field for each face center there. So that's going to give us the, did the wrong thing there. It gives you the cell center value of the face center coordinates of each face center there. So that's going to give us the X, Y, Z coordinates of each face center that we're trying to calculate on. Also, of course, it's a field, so its reference will give us the values there. So that's the vector field reference field equals pointer to this statement there. Then we need to set up the coefficients U0 and M and H. So that's the next three lines. These are the values which Wang has provided for us. And then we need to loop around all the faces in our CF patch here, decide whether or not we are greater than or less than halfway across the inlet of the domain, and implement one of these appropriately. I felt the best thing to do here was to do the exponent separately. So I've created an exponent, a variable called exponent. I'm evaluating it, and then choosing and based on whether or not I'm finding the value of y, and then based on which value of y I've got there, I'm setting my exponent to minus my or minus m times h minus y. I should probably explain why I've got a minus 0.05 here. That comes down to a mistake I made when I was setting this up. If we go back to the domain here, you will notice that the 0 of the origin here is at the top of the step height here. But if you look at my block mesh dictionary, it's actually at the bottom here. So I've got an offset error of 5 centimeters. So I've had to subtract that from my boundary values to get my velocity profile across the inlet. That being so, if I go into this directory, where is it? Here we go, backward facing step coded fixed value. So, not sure if I got it yet, got it mesh. And it runs OpenFOAM like that, and you can see the first thing it did using a dynamic code facility here, it's actually compiling the code I've given it, and now it's running it. And if I leave it to run and look at the flow, I'll actually see that the boundary layer and the inlet section is a lot more realistic than it was in the first case. Now I'm aware that I'm running a little bit slow. I've still got quite a lot of bits to get through here, so I will jump through and I will move on from RANS modeling to LES modeling and talk a bit about what we've got here. Once again, quite a number of well-known models implemented, and I've split them here into algebraic versus transport models. Algebraic, what we've got here is a subgrid scale model. So we're splitting the turbulence into calculated, our simulated grid scale flow, which is turbulence and anything else there. So it's 3-dimensional and time dependent. And then you've got the small scale fluctuations, which have been averaged out by our filtering process and replaced by our subgrid scale model. And that subgrid scale model, in the easiest case, the Smagorinsky model, is just related to the filter function width and the grid scale strain tensor, basically. So it's an algebraic model. You can get away with this because in LES, the amount of turbulence being modeled is much smaller than it is in RANS. Typically 20% of the kinetic energy, only 20% of the kinetic energy should be in your subgrid scale model. And so the importance of the model is much, much less here. Mentioned Smagorinsky saying it's a multi-phase version, must be in one of the multi-phase flow cases. There are problems with the Smagorinsky model, in particular how to set the coefficient. It's very sensitive to that. So there's this dynamic procedure which can be used to do that, and the dynamic Lagrangian model is a variant of the Smagorinsky model using the dynamic procedure along streamlines to make it more robust like that. And then there's the wall adapting local eddy viscosity model, WALE, which I'm going to come back to in a slide or so's time. The alternative to an algebraic model, of course, is to solve some sort of transport equation for K. And we've got all the standard ones. So K equation, a standard model balance equation for the subgrid scale K, or dynamic K equation, which is the same thing, but dynamic procedure on top to evaluate the coefficients. The dynamic procedure, by the way, also has advantages close to the wall. There's also, from a very long time ago, DDoS differential stress model, which basically solves a full balance equation for the subgrid scale stress tensor. A lot of work for not very much return there. Now, I've mentioned WALE, this wall adapting local eddy viscosity model. It's I think it's been put in there quite recently. It's certainly a fairly recent model. And so I thought I would say a few words about it. And if you read the paper, and I encourage you to do OpenFOAM and track it down, have a look at it, the general formulation is to extend the Smagorinsky formulation, but instead of having the strain tensor here, you have some generic space-time operator called OP averaged. And for the whale model itself, they look for a particular type of operator which is invariant to translation and rotation, and a number of other properties easily assessed. We want something we can actually calculate, and a function of both strain and rotation in the flow. So the fact that they're looking for something which is invariant under change of frame indicates you want a tensor invariant, and in fact they trace this part of S and then look at the second invariant of this, which has all the desired properties. Having done that, you have a formulation. You can put that into this formula for the turbulent viscosity. You have this expression, somewhat more complicated, but it behaves better near walls, which Smagorinsky doesn't, and it takes into account both rotation and strain and rotation, which is important for turbulence generation. And my wife's going to get that. I've also mentioned DES, detached eddy simulation, and there are two basic types of model in an OpenFOAM. There's a family based on K omega SST, which can be formulated in an LES formulation, and so can be blended between RANS and LES. And there's another family, very well known, based on Spalart-Almaraz. Mentioned Spalart-Almaraz as a one equation turbulent viscosity model, where you can formulate that in an LES sense as well as a RANS sense, and therefore use it as a blended scheme. Now, in DES, you have a switch to choose which length scale you use: a RANS formulation length scale close to the wall, or an LES formulation length scale in the body of the flow, and that chooses whether or not you're doing RANS modeling or LES modeling. And the exact details of how you switch between those gives you vanilla DES, or delayed detached eddy simulation, or I think it's implicit delayed detached eddy simulation. But anyway, that's the differences between those different models. Okay, I'm speeding up slightly. The pace is great. I'm learning a lot. That's great. I'm glad to hear that. I am speeding up a little because I'd like to get to the end of my slides here. One of the big problems I have with the models in the tutorials which come with OpenFOAM is that the LES cases are two-dimensional. I think that's a fundamental mistake there. LES typically has to be done in 3 dimensions because turbulence is 3-dimensional. One of the other things, so I've constructed an LES case here, and my first action was to take my 2-dimensional mesh and turn it into a 3-dimensional mesh. So extruded it in the Z direction, or rather expanded it in the Z direction, changed the block mesh file to give me 32 cells in the Z direction, and changed the faces, whereas I was using the usual front and back boundary condition to simulate the 2-dimensional case for the RANS case. In LES, I've made them symmetry planes on the front and the back separately. So I've now got a full 3-dimensional calculation. I want to run a calculation, but I need it. I'm going to run it transient as well. And this is going to take a long time to iterate through a lot of time steps. Now, if I start from 0 flow, I'm going to spend an awful lot of time chugging through with the flow developing. So I'm going to do the same thing as I do for my Reynolds stress cases. I actually took my 3-dimensional case, ran a K-epsilon flow case, and used that as a restart, as a starting point. What else do we need to do? Well, at the inlet, we have to inject the flow, and whereas with RANS we can have a steady state inlet, for LES we have to implement the turbulent eddies coming into the domain. There are various ways to do this, and if you get into LES, you'll find it's a complete subdomain of the field, if you see what I mean. So there's a lot of work on things like digital filtering and so forth. I've actually got a paper, a review paper from a few years ago, which I would encourage you to read and cite, of course, going through the different options. But just for the speed of it, and this is not ideal, OpenFOAM has a simple boundary condition called turbulent inlet, which enables you to specify a mean flow and a level of fluctuation, and also a parameter alpha, which gives coherence between time steps. It's not an ideal way of doing it, but it was easy to do, so I put it in there. As I say here, the simulation is fundamentally transient. We need to get to a dynamic steady state, so we need to run for a number of iterations, and then having done that, stop and average and run for some more iterations after that. And I always work out a transit time scale, how long it takes for the flow to go from the inlet to the outlet, and that gives me some ideas to how long to run the simulation for. I need the flow to go from the inlet to the outlet several times for the flow to properly develop throughout the entire domain. So I'll run average multiples of this time scale to reach my dynamic steady state, then stop, restart, and run for averaging. A little bit about post-processing. I think I'm going to have to jump through this quite quickly, but it's a function object called field average is quite useful here, and you can use this to ask the code to run an on-the-fly averaging process. In this case, I've got it just for the U field, and you can specify you want to average to get the mean of the quantity or the fluctuation squared, the average of the fluctuation squared. And I think I've got my average and my square the wrong way around there in the formula, but I hope you know what I mean. So that's basically the variance of the fluctuation. So I've implemented that as a field averaging. Base is in entry base, is keyword base, controls what I'm averaging over here, time step or iteration. And you can specify an optional averaging window. You can control how it restarts by including 3 optional switches: restart on restart, restart on output, periodic restart. Defines what happens to the averaging process when you restart it. Does it try and continue for what it's already got, or does it scrub the slate clean and restart it there? The average field names are constructed from the base field and the averaging type, and information about the averaging is written to a dictionary called field average properties in the time step uniform directory. And one tip here I find quite useful: the API is the programming interface for OpenFOAM, and for all of the main branches it's online, and if you go there it can be a bit confusing. It contains a lot of programming information here, but it does also include a detailed description of what's going on here. So these are the function objects, field average, and there's a whole lot of information, not just about the essential things you have to provide here, but also other options such as restart on restart, which you may or may not want to deal with. That being so, sorry, I didn't mean to do that. I meant to do that. Let's have a look at this. As I say, I've run a calculation here, BS step LES. 0.SimpleFOAM was the results of my initial sign-on calculation, which I saved as a separate directory and copied to 0 before changing everything over to run LES. And if we go to turbulence properties, we should see I'm using LES and I'm using the whale model, but I've also tested it with Smagorinsky and dynamic K equation there. If I go to my 0 file, I've got in the U file here. Oh God, yes, it's a large file. This is possibly not the best way of, but I'll do it another way. Hang around. No. Didn't mean to create a new file there. Minus 100 U. I wish we hadn't put the boundary conditions at the end of files, but tail does enable you to print out the last n lines of something, and that enables me to get to the inlet, which is a turbulent inlet with a given fluctuation scale and a reference field and a value of alpha, which is this time autocorrelation parameter here. And you can see I've got a number of time step directories. I ran it to 5, found it wasn't completely done, so I went to 10, then to 15. 15 onwards, I think the flow is fairly well developed, so I'm in a position to actually run the averaging process from there onwards. But if you look here, so I need 7. I am keeping an eye on the time, by the way. OpenFOAM. Let's go to the end time step quickly. So let's have a look at you. There we go. And you can see here that my flow field is no longer nice and smooth. We are explicitly simulating the grid scale turbulence. You can see there are fluctuations coming in at the inlet. And as the thing goes over the backward-facing step, we're getting eddies which are being carried downstream. Of course, we can also look at the mean flow, and that's much more smooth and regular. In fact, if we go back to, let's go to U, back to the U again. If we go to the 0 time step, we can see the development here, hopefully. There we go. That was my K epsilon calculation. 5-second calculation, you can see the turbulence has worked its way partly down the domain, but not all the way down there, so that's not fully developed. Then 10 seconds, it's got further. 50 by 15 seconds, I reckoned I was pretty much there, which is why I was able to start doing averaging processes there. And of course, that's my complete solution here. If we had time, I could have put it would have been quite interesting to put a stream tracer in here, because it's another way of showing the turbulence here. But let's just do that very quickly. Recent stream tracer. Axis, there we go. 0.2.1. Let's do it here. 1. And 50, there we go. And you can see that upstream of the backward facing step is nice and smooth, but that vortex is much more complicated than we were getting for our RANS case. And let's have some feature eds, and there we go, it's showing the domain, and actually the flow downstream of that is still quite turbulent as well. Just a couple, and I'm aware that we really are coming to I really am running out of time here, but just to show you what else there is on these slides, I spend a few slides talking about different ways of post-processing turbulence, so entropy, but more complicated things like the Q criteria, which are based on the second invariant of the velocity gradient, and what's called the lambda 2 criteria, which is a structure as a vortex if two eigenvalues are less than 0. So if lambda 2 is less than 0. And you can extract these through post-processing, func q, func lambda 2, and you can plot isosurfaces of these quantities in order to identify the vortices that way. The other thing I was going to do here, and I'll leave it with you to have a look at, it's quite nice to animate these things and see how things run just as a transient thing. And the problem with animating LES is you'd want to save maybe 500 time steps, and that would be an enormous amount of data to save. Can we get around this? Well, OpenFOAM does have function objects which do graphical post-processing for you. In particular, there are function objects to do surfaces and streamlines. And you can access these using command foam get and put them into your control dict and run that and run with those in. And every so many time steps, it will save a VTK object, which is the graphical representation of the flow at that point. And you can then open PowerView and have a look at it and see what it looks like. Obviously, you've got 500 of those. Processing all of those to produce images which you can then join up to animate would be a lot of work. So I've got an example here, a cutting plane here. And PowerView, interestingly enough, uses Python as a scripting language. You can open a console in PowerView and run a Python script. And again, there's a link here to the PowerView Python scripting documentation, which shows you how to do this. And if you look in the case here, you will see this is exactly what I've done here. So system control dict. Here is my function field average, and it calls in cutting plane, which is here, which extracts a particular slice down the middle of my domain. But I have also included something called VTK commands.python, which is a script which you can run through PowerView, which automatically reads in the cutting planes, which will be stored in post-processing cutting plane. So it reads in the VTK files from each of these things and writes out the image. The images I put here, and so I joined them all together to make a nice animation. Probably could have got a better output from it than that, but I was doing it late last night, basically. So that is, I think, pretty much all I've got time for. Just a few details there, but thank you for listening to me and really enjoy the workshop. I hope you're enjoying it as much as I am.
Thank you, Professor Tabor. We have 2 minutes left. I think we can maybe answer 1 or 2 questions. Okay, I'm trying to work out. Oh, hang on. If I stop sharing that first of all, that's a good start. And chat. What have we got in the way of chat? Yes, I will share the slides, and if you want to ask me questions, just email me and I'll get back to you if I can, basically. Omega SST, conditions at the far inlet of low turbulence, Omega's initialization works out to be so small, resulting Omega position becomes negative at times. Don't have much experience on that. It is a recognized problem. I mean, that's why you use the SST version rather than the K Omega version. My instinct here would be to do a parametric study to see whether or not a solution, how dependent your solution is on your far fields inlet velocity, inlet conditions as a starting point, basically. But yes, it should work because it should be solving the K epsilon equations in the far field rather than the K omega ones. So it may be that fiddling with the blending factors would be worth doing there. K omega SST DES used for internal flows. My understanding is DES is more for external flows. It's why I was hoping to set up a case to show you, but didn't get around to it. But maybe next year I'll do that. Can random noise generate coherent structures? No, it can't. That's the problem. I did some work on this many years ago. There certainly used to be a mapping procedure, which one process for producing an inlet flow is to run a precursor calculation as a cyclic domain, and OpenFOAM combined that by sampling the flow downstream of the inlet and mapping that back to the inlet. And if it's not there, then somebody needs to put it back in because it's a good way of doing things. Alejandro, yes, there are various turbulence, consistent turbulent inlets. Everybody these days seems to go with these digital filtering processes. Coefficient definition for the whale model. I don't think I've got time. You have a look at what I've got there. Time range for field average. Yes, you can do various combinations of the settings. Look at the documentation, I guess. Implicit LES using OpenFOAM is an interesting question. It's one of the things which I don't think should work, but does. I regard implicit LES the same way as I regard bald as a hair colour. It's not really a turbulence model. Having said that, and I get very concerned about using numerical schemes to do something which you should have a physical model for, basically. Having said that, for a lot of cases, particularly large LES runs, it does give good answers at a reasonable cost. And I'm sure we were all at yesterday's keynote address and saw the issues about the costs of LES still being important here. Well, implicit LES is another solution there. Anyway, it's now 3:02. I don't want to eat into anybody's research presentation, so I guess I should say goodbye and hope to see you around and maybe meet you in the flesh at a subsequent OpenFOAM workshop.
Well, thank you, Professor Tabor, again for this fantastic presentation. I'm sure everybody learned a lot from this. And again, there's some question about the availability of the slides and the recording. I believe they will be online, available on the workshop's website. So please check in later, or otherwise you can send an email to Professor Tabor. Yeah. Again, thank you for coming, and thanks again for Professor Tabor. All right.